see my screen?
Yeah, yes, sir, we can see it.
And see my screen. Okay. Okay. Um, can you still see it? Can you still see it? What do you see?
Yes. We see the university's name and the logo, the first page, digital electronics.
Okay, 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 that's fine. Okay, okay, thank you very much. Um, mm, okay, okay, okay. So I've gotten the number I want, 16, so we can start. So today we're looking at just the course outline, right? The course outline of for digital electronics, what to expect from digital electronics, and what when you finish the course, what you are expected to know, you're expected to do, and then the learning outcomes as well. So this we could see the Ghana Communication Technology University, the badge, then Institute of Distance Learning. Yes, so you guys are the distance learning people. And then sorry for the BS Information Technology. I know you guys are DIT, right? Are you guys DIT?
Yes, sir.
Yes, sir.
Yes, DIT. So basically it's just the same thing. You guys, DIT and then BSc are using the same course outline, the same teaching method and all this things. So it still applies to you guys. And then you will see the main title, which is digital electronics. So this course is a level 100 course. Then the academic year should be 2025, 2026. Sorry for that. And then 2 credit hours. And the lecturer's name is my name, no, Dr. Agyeman, mobile. There is the number and then the email. So if you have any question, any problem, any challenges in this course, you can email him through this number. So we'll look at the course description. So basically, this course introduces you guys, or this course will introduce you guys to how digital systems work, right? Currently, our systems are moving from analog towards digital. So we'll look at how digital system works. Then I'm coming, hold on, I'm sorry, I'm coming. Yes, so this course will introduce us to how digital systems work. And I said almost every modern electronic devices, such as computers, calculators, phones, even traffic lights, right, and digital clocks, and even microcontrollers operate they operate using digital signals, right? So in this course, you know what a digital signal is, what analog signal is, the difference between digital signal and then what analog signals, and even discrete signals. And in this course, we shall learn how information is represented using what zeros and ones. So when I say zeros and ones, it's basically binary. Most of our digital system, they understand digital signals. And then digital signals uses what we call what zeros and what ones. From our SHS, we know zeros and we can do what binary, we can do binary to decimal conversion. So the zeros and then the ones are what we call what the binary. And then how logic gates make decisions. So we look at what is logic gates, right? So logic gate is basically the fundamental unit of what digital signals. So almost all the computers, the calculators, the phones, the microcontrollers we have in our systems now, they make use of what you call a logic gate. And then in this logic gate, you have what you call a combinational logic gate and then sequential logic gate. We'll look at that one as well. Then we'll look at how circuits are designed. How circuits are designed. Then memory-based circuits. So when you say memory-based circuits, we say we have what you call flip-flops, right? Flip-flops. So memory-based are basically sequential circuits. So look at that as well. Look at registers, look at counters. Then what I want to put across is this course is not only theory-based, like what I said, it's not only theory-based. You can also look at the practical aspect where we do programming hardware such as Arduino, and then the other programming languages, C++, basics, then VHDL, Verilog. They are all something we look at. They are all something we look at. So our next will be what the course objectives and learning outcomes. So when you go through this program, this course, what should be your what should be the learning outcome for you guys, right? So our first topic will be knowledge and understanding. So you have to appreciate what is called the fundamental digital logic. And I said fundamental digital logic are just what the logic is, and then there's the fundamental unit of what any digital circuit. So need to appreciate. So we look at when we say appreciate what the fundamentals of digital logic. So basically, what this means is you need to how does computer understand information? We know our computers they do not understand our names. Like when you say something into our system, let's say how are you? How are you on our computer or any social media platform? They do not understand what how are you is, but it's the computer has what we call the logic gate that converts what the information to binary numbers, right? Binary numbers. So it represents the information to zeros and ones. That will help the computer to understand what you sent, right? And then, like I said, this will lead towards number systems where we do binary to octal conversion, hexadecimal conversion, the ASCII code conversion. ASCII means ASCII is ASCII. So American Standard Coded Information Interchange. We'll look at that as well. We'll look at gray code, then look at parity check, and then CRC. Look at CRC. And then I say this one, we look at the difference between analog and digital signals, then why binary numbers are important, right, in computing. And how, like I said, how to convert between decimal, binary, octal, and hexadecimal. How logic gates are used to build circuit, and how Boolean algebra, when you say Boolean algebra, they are just expressions. Expressions. It can be in the form of A, B, C, D. Boolean algebra that helps simplify digital circuits. Then our next topic, our next subtopic will be intellectual skills. So you need to know how to design fundamental blocks. So after going through the knowledge and understanding, you should know how to design fundamental building blocks of modern computers, such as the arithmetic circuit. So when we say arithmetic circuit, we have what we call full adders, half adders. So the full adder basically is the addition of three or more inputs. So in that three inputs, we have the input part and then the carry in. So that will produce a single output, right? We produce a single output, which is the sum and then the carry out. We have under the arithmetic circuit again, we have half adder. It only adds two inputs. So we look at that Then we look at code converters. We have the encoders and the decoders. Then multipliers. Then after that, you have to combine all these fundamental blocks to get what a complete digital systems. Combine all these fundamentals to get a complete digital system. So all what I've said is basically to tell you how you, after learning all these things, you need to know how to design a simple arithmetic circuit, build a truth table, form a problem statement, right? You need to know how to build a truth table from a problem system, convert a Boolean expression into a circuit, then also combine gate to form what complete what system. Look at the practical skills, right? The practical skills basically, I said earlier, it's not going to be theory based, right? It's not going to be theory based. You are going to, it's just, you are going to relate whatever the theory based you have done to the practical world, where we look at how to display LED display. So if the LED ons, if LED on, it means what, the binary number 1. If it is off, a binary number what, 0. Then we'll look at Arduino Uno. Arduino is just a board that helps you to do connections from that board to a breadboard, right? Those in the electrical department, when I say breadboard, they know that. They know what this thing. Then we'll look at what counters, right? So the practical word is counters. The counter is basically, that's what we call counting. That's what we call counting. So we look at all these things under what practical skills. Then under the transferable skills and then personal skills, look at how to write a technical report. So after doing your connection, you should be able, or learning the practical skills, you should be able to write a technical report of whatever you are getting, the displays you are getting, right? And then you should be able to use what you call these softwares, something like softwares and hardware language, such as the C++, the C or C++, and then the VAD, or they are all the Verilog, they are all programming languages. Then we look at the course requirement and policies, right? This is just a predicate of what analog electronics, basic programming. So in your earlier if you in your earlier studies you've looked at analog electronics, this is a build up to what the digital electronics is a build up on what analog electronics. So in analog electronics you look at what analog systems, but in digital electronics you look at what digital systems, how the digital systems operate based on their logic gates and then all. Then we look at the basic program, right? C++, I mentioned already, C++ and all. Yeah, and these are the teaching and learning methods. So it's going to be more of what teaching will be in lectures, right? So it's going to be sometimes going to be face to face, sometimes going to be online. Then it's going to be interactive. So it's not going to be like I will come and then I'll talk. No. It's going to be what interactive teaching. So I'll ask question, then you answer, then we'll move ahead. I'll give assignments or try work, you try, and give me my solution. Then what I mark. Right, so it's going to be something like that, interactive for teaching. It's going to be what a presentation mode as well. So sometimes I give you assignments, a presentation, you work on it, then you come and present to the class. Don't ask questions under them, then we'll give you a score. And then collaborative learning, it is more of what the interactive teaching. So we'll collaborate. It's not going to be like I will come, then talk, and then end the class. No. So always need to what? Need to be ready for whatever is going to come. Even without me teaching, you should be what ahead of the class so that the teaching will be easier and then faster. Then lab session. So lab session is basically what the practical aspect, where we look at the Arduino, we know the programming languages and all. Then we'll build mini projects. The mini project how to what display some example can be how to display the LED. If the logic is on, the LED will display will light up. If it is off, the LED will go off. Then we'll look at these connections on what the breadboard and then what the Arduino as well. Then these are the learning materials, right? So you can go online and then download these things, fundamentals of digital logic with VDH. So I'll if I get the time, I will send you these learning materials, right? These learning materials. So they are three. So there are three. You can check them out on the internet. Sorry, I check them out on the internet. So there are three. So these are the materials we'll be using for this uh course. Nothing will come. Nothing will not be from this side. Everything will be from these textbooks or these materials. And then these are grading criteria. So the grading criteria, we have our midterm exams, which will be 20%. 20% of your what? Your mark. So the midterm is not going to be like so it's going to the midterm is going to test your early understanding of what number systems, logic gates, Boolean algebra, and then a K-map. So look at K-map. K-map is just basically what a canal map. So K-map is it's just a graph. It's just a graph or a map that what simplifies Boolean expressions, right? So look at that. So the midterm, which is 20 marks, will test your early understanding of what number systems, logic gates, Boolean algebra, and then what K-math. Then we'll look at lab sessions and attendance. So it's going to be 10% of what your score. The lab sessions and attendance, sorry, is going to be 10% of your score. So it's going to reward practical participation and consistency. So whatever we do, any lab session and then attendance we take, you need to be what always present. You need to be involved. If not, you're going to lose a whooping what 10%. Then assignment and quizzes will be 10% as well. 10%. Then we'll look at end of sem exam. So end of semester exams is going to be 60%. So 60% of your score is going to what end of semester exams, and then assignment and quizzes 10%, lab sessions and attendance is 10% as well, and then mid semester exams is going to what 20% of your score. So like I said, we should not wait until the final exam before learning, right? This is something from me. You should not always what wait until final exams before you start learning. I mean, people are last minute learners. Some people are last minute learners, and I tell you, this program or this course is not going to permit that because this course is progressive, right? So it's progressive. Like I said, if you don't understand number systems, Boolean algebra was difficult. So it's going to be a build up of whatever we do. So whatever we start with, you should be able to understand it before we progress to a different place. So if you don't understand, for example, a number system, learning Boolean algebra is very, very difficult, right? And even if you don't understand Boolean algebra as well, key map and then circuit design will also be difficult. So it's going to be a build up of that. So always be current. Be current. You shouldn't wait until exam before you start learning. So this is something from me, and I hope you take it as well. I hope you take it as well. Please, can you hear me?
Yes, sir.
Yes, sir.
Ah, so I hope you take what this should I say advice? Yes, this advice I've given you guys. So always be current, always learn because it's progressive. One topic depends on the other. So if you don't know, or if you don't understand that topic, that learning the other topic is going to be difficult. Going to be very, very difficult. So understand the first topic and then we go to the the second topic as well. And then this this is now our topic and our course schedule, right? The topic and course schedule. So week one will be a topic of introduction to digital electronics. So each content is what you understand the difference between what digital systems and then what analog systems. What goes into the digital system, and then also you could see from this this graph or this axis, you could see more of analog, right? You could see the signal is moving from this direction and then continue this direction. This guy is going. This is what we call what analog signal. Right? They are analog signals. Then we look at this is also what digital systems. You can see this is a 1 and this is what a 0. This is a -1 and this is what a 0. So it represents just a high and a low. So these are what a digital system. These are what we call a digital system. So we look at the concept between what a digital system and what analog system. So we look at examples of what digital systems or analog systems, right? We look at examples of that. Then we look at noise margin. So how noise, we look at how noise affects what digital systems and then how noise affects what analog system. We say in digital systems, analog in digital system, noise do not really affect the signals like that because even if it affects it, it's easier to what recover the signal back because we need only what we call it an amplifier to recover the signal back. By analog signals, systems or analog signal, noise affects it. Any small noise will cause a change in the signal, and then it's very difficult to recover the signal back. So look at the advantages. The advantage of what a digital system have or what analog system, even though they are advantages over what advantages of digital system over analog system. There's there are as well the disadvantage of what digital systems and what analog system. Then we look at that. The disadvantage we can see, let me give you one. We can see digital system requires what we call synchronization. So in our computers and calculators, we require what we call synchronization. All the components in the digital system depends on the other. So without synchronization or without a timing between the system, you cannot get the output you require because one system cannot work while the other system would become obsolete or become ideal. They must work in hand in hand. But in other systems, it's not like that, right? So we say a digital system gives out or it allocates a resource, each resource towards synchronization. But in another system, it's not like that. It varies. It doesn't depend on what analog with synchronization. So this one of one disadvantage of a digital system over analog systems. Then we look at digital words and prefixes, right? So this digital word is just literally how are you will just be converted to what a binary number. Then look at that. Then we look at the transfer of digital data. So the stages between the transmitter and then to the receiver. So the transfer digital system. So in a digital system, we have several stages and a signal will go through before it can be converted to it can reach the receiver, sorry. So we have what we call in one example, one block can be an encoder, right? So the encoder basically converts the signal to what the binary zeros and ones. So we call it a bit stream, right? So it converts. Then we look at what we call pulse modulation. So it goes through the pulse modulation, which amplifies the signal or it modulates the signal before what going through the channel. So where the channel basically is that the path with the signal travels. So the channel can contain a lot of noise, right? So a lot of noise. If there are a lot of noise in the channel and then the signal passes through it, it might now come to the demodulation part where it recovers the signal towards the bit stream again, and then the decoder converts it towards analog signal. So look at this, the transfer of what digital what data. And then with 2 and with 3, we look at number systems and code. We look at how to convert binary numbers to octal, binary numbers to decimal, binary numbers to hexadecimal. We don't look at the vice versa of that one as well. We look at octal to binary conversion. look at hexadecimal to binary conversion. Then we'll look at octal to hexadecimal conversion. Then we'll look at hexadecimal to octal conversion. Look at that one as well. Look at subtraction with complement. So when we say complements, we have two complements. We have one's complement and then two's complement, right? So the two's complement is gotten from what? The one's complement by adding a one to what? The one's complement. So a one's complement, basically you change the bit stream towards the vice versa. So if you have, like you see, you have zeros and one, for a one's complement, it's going towards one and what? Zero. So look at that as well. Look at sign bits. Sign binary addition and subtraction, right? The sign basically means representation of binary numbers in what? In their negative form and then a positive form. So if the leftmost bit is 0, it means a positive number. If the leftmost bit is 1, it means what? A negative number. That's what is called sign binary addition and subtraction. Then we look at overflow, and then arithmetic code, then ASCII code characters, character codes, Greek codes, and then CRC. We look at them as well. And then week 4, we look at binary logic and gates. So under the binary logic and gate, you have the basic gate and then the universal gate and other gate. So the basic gates are what you call what? The AND, the NOT, or OR gate. So AND is just a multiplication of what? Binary of gate. Then OR is basically the addition of gates. And then the NOT is just the complement of gate, right? And we have the NAND gate and then OR gate. So the NAND is basically the complement of AND gate, and the NOR gate is basically the complement of what? OR gate. When I say the complement is just what? The addition of the NAND is just the addition of what? AND and then NOT. And then the NOR is what? The addition of what? OR and what? NOT. So look at the other gate as well, which is the XOR. So we say XOR is basically what? Exclusive OR. Then XNOR is what? Exclusive NOR. So look at that will be done in what? Week 4. Under that, we have what we call what's the symbol representation and then the Boolean algebra for both of them. So we'll look at the symbol representation as well. We'll look at the truth table as well. Truth table of these gates, I've mentioned. Then we'll look at, that said, we'll look at the Boolean algebra, we'll look at algebraic multiplication. So it's basically the simplification of what? Boolean algebras from truth table and then from Boolean expressions, right? Look at that. And then the complement of a function is basically what I said, the NOT. Look at that. And we look at sum of products and the product of sum in the standard forms and the min terms and max term. So the sum of products is basically the addition of the product of what? Boolean algebras. And then the product of sum is the multiplication of addition of what? The Boolean algebras. And then the standard form is that the simplified or the minimum state sum of product or the products of sum can be. Then we look at the min term and then the max term. That will help, that will propel us to what we call what? The K-map, which will be done in what? Week 5. So the K-map, we'll look at K-map. So the topic will be K-maps with simplification and other derived gates. So we'll look at the two variable K-map, right? So under the K-map, we have different representation. You have the 2 variable K-map, we have the 3 variable K-map, 4 variable K-map. We'll look at that as well. We'll look at the simplification, how the simplification is done under the K-map, how we group bits before it can be simplified under K-map. And I said K-map is just for what? Minimization of what? Boolean algebra, or simplification of Boolean what? Algebra. So look at that. Then we'll look at what exclusive OR gates. How exclusive OR gates are represented on the K-map. What their K-map is about. And then NOR gate as well. NOR and OR gates as well. Then week 6, we'll do what is called combinational logic circuit, right? Combinational logic circuit. So under the combinational logic circuit, like I said, we have what we call the adders, right? We have the full adders and then the half adders. So as I've explained that already, the full adder adds for 2 inputs. So the two inputs can be what? A and B, and then the carry in. And then the half adder can be the half adder basically addition of what? Two inputs. So we look at the analysis or and then size procedures. We look at their how the full adder, then the adder, half adder, that's the what? The addition based on the what? The truth table, and then look at their Boolean function as well. Like this is the second point. That's what the second point means. The verification of Boolean functions and the verification of what? The truth table. Then we look at how after going through these 2 points, look at how to design the what combinational circuit, the symbol representation, the Boolean expression, and the truth table. That is what we call a design of what combinational what systems. So that will be what for week 6 and week 7. So this is it. Week 7, you have what you call the half adder and the full adder, sorry. Then this is also a different arithmetic circuit, which is the parallel adder. So the parallel adder is usually what does multiple what additions. So like I said, the full adder does what 3 inputs addition, and the half adder does what 2 input addition. But the parallel adder and then subtractor, it does what we call multiple additions, which can be 4 or more. Then we have the multiplier and the multiplier. So the multiplier is basically what a circuit that what that produces a single output from what a multiple single input is multiple input, sorry. So it produces a single output from what a multiple inputs, and then the multiplier is going to what the reverse of what multiplier, where it produces a single input from what a multiple what output, right? Then week 8 will be midsem. So your midsem is from week 1. It's going to what week 1 to week 7. That was the midsem exam, which will be under what week 8. Then the same week 9 as well is going to what midsem as well. It's going to be the same. So the midsem can be held on week 8 or week 9. After the midsem, then we'll come to our week 10, which is what sequential circuits, right? So a sequential circuit basically is a circuit which depends on what the past state and then the previous state as the past state and then the present state. The arithmetic circuit, sorry, the combinational circuit, it depends on what only the previous the present state, sorry, depends on only the present state. But the sequential circuit, it depends on what the previous state and then what the present state. So under the previous sequential circuit, we look at latches. So we say sequential circuit have memory, right? When you say it have memory, it has memory of what the past state. So we look at latches. We look at the symbol representation of latches, the truth table, the Boolean expression for latches as well. We look at the flip-flops. So we get flip-flops from what latches, right? And at that as well, we look at the symbol representation and then the Boolean expression and the truth table. Look at the master slave flip-flop, right? The master, we have in that flip-flop, we have what we call the master, and then we have forward the slave. The slave depends on the master. We'll look at that one as well. We'll look at edge trigging, right? What edge trigging basically meaning flip-flops. And then we'll look at analysis with what D and J flip-flop. These are different types of flip-flops. So under the flip-flops, we have what JK flip-flops, and then the what D flip-flops. Then we have what we call SR flip-flops, right? Then week 11, we look at sequential circuit 2 as well, where we look at designing a sequential circuit with D flip-flops, and then what designing with what JK flip-flops. So look at that. I know these are sounding some ways to you, but when you get into it, you appreciate whatever the course outline is saying. And then week 12, look at registers. So registers are just an it's just example of what sequential what circuits. So registers basically are working from what we call flip-flops. So we look at registers with what parallel loads, and then we look at shift flip-flop, serial transfer flip-flop, serial serial addition registers, shift register, and then parallel load registers. Then we look at bidirectional registers, right? We look at them as well. And then week 13, which will be our final week, will be what? We'll deal with what we call counters. So there are several counters. So basically, a counter is what it's just a circuit that does for counting. So it can do counting from 0 to any number you want, 0 to 10, 0 to 11, 0 to 15, all that. So there are different types of counters. That's what we call, we have the binary array counters. Then we have the up and down counter. So that one does a counting from the higher number towards the lower counter, the lower number. So then we look at BCD counter. Basically, BCD counter basically means what? When the counter reaches a binary number 9, it must what? Add something, it must add a logic gate to it. Then it reverts back to what? The starting point. So that's basically what a BCD counter. So this will be our last final what? On our last final we'll do what is called counters. We'll look at them. I mean, it entails a lot. It entails a lot. That's what I said. Whatever we are doing, whatever we do, when you are doing, we do something in week 1, then week 2 will be what? A build up on what we did in what week 1. So in order for not else to be what left behind, we should always what be present. We should always attend to us. We should always understand what these things are before you get yourself what wanting. So like I said, when you don't understand something and then you just leave it like that without asking any question or without showing any willingness to understand, then whatever you do in the subsequent week, I'm sorry for you, you will not you will not understand, you will find yourself wanting. So like I said, I'm always around if there is any help, if you need any help concerning the topic, I'm available. You can come to me or you can text me or you can email me. Then we'll look at that. All right. We'll look at it and then will make your stay in this school very what interesting and then I know you guys are working and then there's pressure, but I'm pleading in order for us not to be left behind. We should always what should always be present. We should always understand what you are doing and ask a lot of questions, right? Whatever is bothering you, ask a lot of questions and then ask the questions and then you'll be good to go. You'll be good to go, right? So this will be this the end of our course outline. If there's any question for me, please ask. And then if there is nothing as well, let me know and then we end the class. Then we'll look at we start by looking at week 1 from next week going, right? So any question for me, please? Any question for me? Hello?
Yes, sir, we can hear you.
Any question for me, please?
I think it's clear, sir.
You are clear with that, eh?
Yes, sir, please.
Okay. Any other person? Any person? Hello.
Um, Everything is okay, sir. We are good.
You are good, eh?
Yes,
Okay,
sir.
okay. So we'll end the lecture here. Then we take it from there from next week going, right?
All right, sir.
Okay. Thank you very much and have a great weekend.
All right,
Bye.
sir. You too.
Okay.
Bye.
Bye.
Bye.